Recorded, rolling. It's Friday, February 6th. Yeah, so sorry, I haven't been able to be here the last couple days. Not feeling too good, but yeah, getting up to you guys a cool day. So, yeah, last couple days, you guys did these droplet puzzles. Right. So, I did get these graded and back in your return folder, so you guys do have these. Right? And yesterday, you guys watched a cool documentary piece on Alfred Nobel, what he was researching his life. And so, all the papers that you guys had turned in up to yesterday, yeah, I've got graded and returned back to your folders. So, those are there for you guys. You guys can get those and say what you need to study. Right. So today we're just gonna uh, solve a bunch of these chapter 14 and 15 puzzles. So chapter 14 in your book is about vibrations and waves. Chapter 15 is specifically about sound, so kind of a subset of waves. Okay? Now, if you want to, you guys can hold on to your work today because you might want to study it over the weekend. The quiz is going to be on Monday. Right? So quiz on Monday. Right, any questions about what we're doing? All right. Right, so I picked out some ahead of time that I thought looked pretty good. I know we did solve some of these a few days ago. I think these first few, up to like the Sears Tower and also this earthquake. But we did those before. Right, so let's say how about 76 here? It says ocean waves. An ocean wave has length 12 meters. A wave passes a fixed location every 3 seconds. What's the speed of the wave? Right, so here I'm gonna draw that out, tag some numbers to it. Let's see what we got here. Right, so we're watching these ocean waves come in. We can look something like this kind of from the side. And we're saying from crest to crest, that's one wavelength. Guys, do you remember what Greek letter we're using for wavelength?
Did you do the other?
Like lambda? Oh, wait, what's that?
Other one? I remember I was doing something, but you said I could just copy it.
And so this is
69 out of the class there,
Wavelength.
74.
uh it says from crest to crest is 12 meters. So 12.0 meters. Right? And then let's say that what if there's like a like a dock right here, right? We're walking along the dock, right? And we're watching the waves crash, and we're counting the amount of time that it takes, and the time period is like 3 seconds between crashes every 3 seconds. Okay? And the question is, what is the wave speed? What is wave speed? Okay. Now you might be able to get it, just look at the numbers I wrote down. Can anybody just look at it and realize what the answer is? Mhm. Okay. Because think about units. What's the units for speed? Meters per second? Do you guys see some meters and some seconds going around?
4 meters a second.
There you go. So the answer has to be 4 meters per second, right? Okay. All right. Now, I want to take you guys through a little bit longer way of going about it. Okay. Uh, actually, it's a good review for frequency anyway. Guys, what is frequency related to time period?
Uh, 1/t.
Yeah, 1 over the time period. Okay. Uh, for example, if you guys heard like 4 beats per second, then the frequency could be 4 hertz, but the time period between beats would be a quarter of a second. Okay, so these are reciprocal. So if that's true, then what's the frequency in this case?
Uh, hertz.
Yeah, a third of a hertz. Right? Wouldn't that be true? A third of a hertz. Okay. Right. Okay. So why am I going down this path? Because there is a wave equation that can also answer this question. You guys already told me the answer. It has to be 4 meters per second. You said, oh, 12 over 3. Okay. But another way to get there is say speed equals. Does anybody remember a certain wave formula? Speed equals what times what?
Is it just frequency times time?
It's like wavelength times frequency.
Or
Wavelength times frequency. Right? So let's try it with this method and see if we still come out with 4 meters per second. So I'm going to take this crest to crest distance of 12 meters, multiplied by this frequency of a third of a hertz. Yeah, and hertz is 1 over second, so this the units still work out. And it is 4 meters per second. Right? So a little bit longer way of getting there, but of course it's the same answer. I would take you guys through that proper wave formula. Right? Alright, so that's a pretty good warm up right there. Alright, you guys good on ocean waves? Alright, number 77. Water waves in a shallow dish are 6 centimeters long. At one point, the water moves up and down at 4.8 oscillations per second. What's the speed of those water waves? And what's the time period of the water waves? Alright, so this sounds fairly similar. Say 77. Right. They've got a dish. Okay. I'm like zoomed in on this dish right here. Okay. We're watching these little ripples go across. Right. So it's like watch these ripples propagate. Okay. And from crest to crest, let's say this wavelength is 6.0 centimeters. Right. So you look into that. Uh, and it also told you, guys, 4.8 oscillations per second. What does that describe? That's a what? Frequency. Yeah, that's a frequency. Yeah. So I can say the frequency is 4.8 hertz. Right. Well, yeah, I just gave you guys or we just used this. Speed is wavelength and frequency. Right. So you know that. Hey, we got wavelength, we got frequency, but we can just plug this in. Let's go 6 centimeters, 4.8 hertz. It comes out of this. This would be centimeter per second. Okay, about that. Okay. That was question A. Question B says, what's the time period? Okay. Oh, but guys, how do you get time period again?
One over.
One over the frequency, yeah. Yeah, so frequency, time period are reciprocals of each other. And so let's try that. Let's do 1 over 4.8 and then hertz right here. Okay. So I'm looking at 0.208 and then the seconds because it's first two atomic. Yeah. Right. That's really close to 1/5 of, I mean, right, 1 over 4.8 is really close to 1 over 5, right? So approximately every fifth of a second, or you can say 5 times per second, maybe these crests are like slamming up against the wall of the dish. Yeah. It's a little ripples right there. Yeah, got that. Number 81. Speed of sound in water is 1498 meters per second. Ooh, see if you guys remember a little bit of trivia. Back to the last lab you guys did a few days ago. Because what's the speed of sound approximately in air? Like, huh?
480, right?
Yeah, I think it's around,
342.
yeah, 340, 343, somewhere there. We've been using. Yeah, so like in the terms, probably in the 340s. Okay, so where is sound faster? Air or water?
Air.
Huh?
Water, air. And water.
It says right here, it has to be water.
Yeah.
Yeah, multiple times, isn't it? Yeah, 1498, that's a lot faster than 340. Yeah, a lot faster for water. A sonar signal is sent straight down um, from a ship. Okay, just below the water surface, we'll call it water surface. And 1.8 seconds later, the reflected signal is detected. How deep is the water? Might help to draw this one out. The 81. Okay. So, say we got, here's the ocean surface. Okay. You got the seafloor down here. Here's the ship. Okay. And we're going to send a signal. It's going to go all the way down to the ocean floor and then boom, it bounce back up, reflects. Ooh, maybe like an echo. Looks like an echo, doesn't it? Okay. And I know that the speed of the wave is 1498 meters per second. Now, I'm gonna call the time t total because it is a round trip, isn't it? Doesn't the signal have to go all the way down to the floor and back up, be detected? Was 1.80 seconds. Call this D for depth. So what's the depth? How do you guys think we could find that?
Velocity times time divided by two.
Exactly. Yeah. Right. So I can say that the total distance moved, which is actually 2D, isn't it? Right. So there, that. Okay. So it's like distance equals speed times time. Right, we should probably know before you walk through this class, but it is a two-way distance, and we only want the one-way distance, which would just be the depth.
The t by 2 lengths.
Speed times time. Yeah. Right. Or this t and then divide by two. Yeah, you could do that too. Yeah. So like that.
Couldn't you have just divided the total time by two before you started this?
Yeah, that's another way you could think about it.
Okay.
Yeah. So what Kai's saying is, well, if you know the total time, you could, yeah, cut that in half and say, well, maybe it takes 0.9 seconds for a one way. Right. Kind of focus on like this fraction right here. Yeah, you can do that. Let's get you there. All right. So number 88. What is the time period of a pendulum with length 1.4 meters? $88. Okay, so length equals 1.4 meters. Okay. Let's make some assumptions here. There's one assumption what's one assumption do you think I'm gonna make?
The gravity's 10 meters a second.
Yeah, let's definitely assume we're in Earth gravity. Yeah, you call it 10, so let's go to 10. Let's do that. Oh, what do you think's some other good assumptions? That's some technical thing. Actually, that was probably the most important one.
We could just make the weight something like 5.
Yeah. Most importantly, the significant mass is all located in the spot, and the string is relatively massless. And also like no air drag and blah blah. But yeah, so we got some assumptions. Um, I don't think I would expect you guys to memorize this, but yeah, be able to apply this. This is some version of this right here. This was the answer to one of your labs, right? This. So let's apply that. Let's say time period is 2 pi square root over 2. Right. Let's see if we're all coming up with the same thing here. Make sure you can plug this in your calculator and get the parentheses correct. Because yeah, some students don't put the parentheses in the right place and then work out right. Right. Right, so I'm getting a number. What are you guys getting?
2.35.
Okay, yeah, that's what I got too. 2.35 seconds. Yeah. Now, here, let's put a little context that make sure it makes sense. Right? There's 1.4 meters. That's like almost as tall as a person. Right, so it had a pendulum that was like almost as that was as long as almost as I am tall. Right. Right. Looks like it would take. Well, yeah, there's 2.35 seconds. Is that the time from the left side to the right side and then back to the left again?
Yes.
Yeah, it's one full cycle. Right. So if you cut that in half, looks like a little more than 1 second to go to the right and another more than 1 second to go back to the left again. Yeah, I think that looks about believable. So that looks about right. All right, number 90. Wait a minute. This is a yeah, okay. Radio wave. AM radio signals broadcast at frequencies between 550 kilohertz and 1600 kilohertz and travel at 3 times 10 to the 8 meters per second. Okay. Hey, pause right there. You guys see that speed right there? 3 times 10 to the 8 meters per second? What's special about that speed?
That's good, Mike.
That is the speed of light. Yeah. Wait a minute. Is that true? Do radio waves travel at the speed of light? Yeah, they sure do. Yeah, the speed of light is really the speed of uh, all amounts of particles and all electromagnetic waves, which includes radio waves. Yeah, that's true. Right. So, what's the range of wavelengths of these signals? And then question B is about FM stations. So, let's start with the AM. We'll try that. Right. So, let's go. Speed equals wavelength times frequency. Okay. Now, it's a special speed. Okay, so these are all EM signals. So, we'll call it 3 times 10 to the 8. That's meters per second. Yep. The speed of light, speed of radio waves, same thing. Okay. We want to know what's the range of wavelength. So, well, let's write one frequency at a time. So, one end of the spectrum is 550 kilohertz. Okay, what does kilo mean? Kilo is a what?
1,000.
1,000. So I'll just go ahead and tag on 3 more zeros. Hertz. Yeah. Yeah. Now that would be, let's see, I think that would, well, that would be the smallest frequency, so this would be the longest wavelength, should be. Here, I'll call this like long. Okay. And then we'll have to solve this again to get the other end of the spectrum. So same speed. Okay. These are all traveling at the same speed. But what's the short end? And that one was 1600 kilohertz. So again, we'll tag on 3 more zeros for kilo, and they call that hertz. Yeah. So, okay. Then, ooh, maybe I should write it this way. Lambda is between something and something. Okay. We got the long wavelengths, we got the short wavelengths. Okay, we're gonna find out. Okay. Alright, so in parentheses here, here's the speed of light, speed of EM. Okay. I divide down. Oops. The frequency. Okay. You guys know I'm just going to divide over the frequency of both of these, right? Okay. Right. What did you guys get for the long wavelength?
45.45.
Okay, yeah, that's what I'm getting to. 545 meters. Ooh, 545 meters. Right. So if you're tuning in AM station, you could be tuning into radio waves that are hundreds of meters long to get those signals. Right. Well, but what's the short end? How short can these go? Well, divide over this other frequency. So I'm just going to divide this over. Okay. 187. I'm rounding a little bit, maybe to the nearest meter. Okay. But to the nearest meter, somewhere between there, that's kind of your spectrum for AM stations. AM. Okay. Uh, I usually listen to FM radio myself if I'm listening to something. So I'm actually more curious about question B, which is kind of the same premise, but it's for FM stations. Hey, do you guys ever well, you guys probably listen to FM, right? But what are the dials turn to? It's like from what to what?
Different channel. Stations.
Yeah,
Like numbers you're talking about?
yeah.
1,000 pixels?
That's like right here, from about 88 to 108. Yep. It's actually like 87.5 to 107.9. Right? Like if you want to broadcast anything in the United States, right, and then store and buy a radio that's kind of tuned into something, right? Like you could tune into like 96.5 out there, like that could be a station, right? Right? But it has to be somewhere basically between the two. And your book are rounding a little bit. So let's use your book values. Approximately 88 to 108. Like you can't tune into like 111, right? That's just it's not a standard that we have, right? Maybe in another country. Right? But those numbers have units. Guys, what are the units on those stations? It's right here.
Sorry.
Yeah, megahertz. Yeah, MHz, megahertz. Right, it's a little bit blurry, but it is megahertz. And what is mega? Mega is a what? Starts with an M. Million. Yeah, million. Right, it's like millions of hertz. Right, so let's basically solve this, except for the FM stations. Right, so this is 90B. So this is FM stations. Okay. So we're still doing speed equals wavelength times frequency. Okay. And we still got, guys, is it still saying speed of light?
Yep.
Yep, sure is. 3 times 10 to the 8 meters per second. That's how fast those are traveling. Okay. And I'd really like to know wavelength. Right now, frequency could go anywhere from, we'll call it 88 times 10 to the 6 hertz. We'll cross out the other equation here. And that's 108. Again, 10 to the 6 hertz, because that's what mega or a million is. It's 10 to the 6. Okay. Right, so just like before, this will be the long wavelength. This will be the short wavelength. Okay. So I'll say the wavelength that you're tuning into for FM. Okay. Okay, so the one was AM. We'll go ahead and label it AM. So the one before is AM. Here's FM. It's got to be between what and what? How many meters? How many meters do you think? Huh, why those wavelengths coming up? Okay. I bet if I had a radio right now, I could tune in. I bet their radio waves are passing through the ceiling, and we could tune into whatever station being broadcast in Florida right now. So type in the speed of light, 3 times 10 to the 8, close parenthesis, and then divide. Let's divide over the frequency. So open parenthesis, 88 times 10 to the 6. You know, this should be the long wavelength, so I'll put that right here. Okay. What are you guys getting for the long end of the wavelength?
3.4.
Yeah, yeah. Ooh, 3.41 meters. Well, that's way shorter than the AM waves. Okay. I wonder how short they can go. Well, that would be answered by this other setup. So I'll scroll up, scroll over where the 88 used to be. I'll just replace that with 108. It's still 10 to the 6. I'll get that. Okay. What do you get for the short end?
0.78.
Yeah, it looks bad. 2.78. That's also meters. Okay. Okay. Well, that's yeah, more comparable to like the width of this room, like about 2, 3 meter. It's about 3 meters somewhere in there. Yeah, about 3 meter long wavelengths. Yes, good. All right. Let's do a Doppler question. Doppler. Actually, since we're about to switch to Doppler question, they're great details here. Okay, so you guys did pretty good on these. Of course, we're about to do one of these basically. Okay. So these Doppler questions, just to hit a couple of these here. A lot of you guys got the Hill question. Some of you guys this though. Now, this didn't have the extra trick of what did you have to solve for first before you can solve for the frequency? Yeah, the speed of the car at the bottom, which doesn't involve gravity, right? If he was just coasting down, he's building speed the car the hill is. You guys, what's the speed of the car at the hill about? Based on the height of the hill? It's like square root 2GH. Guess where that it was an expression that showed up over and over last semester. Everybody had a different height hill, but in general it'd be square root 2GH. And then you could run Doppler for that. Right. The other one that was which I think only a couple of guys got this other one is this one with the rocket boosters. Okay, what was funny about the rocket boosters? Did anybody notice this was kind of a trick question?
Yeah.
What was tricky about it?
Was asking with this. That's where it was inside the car.
I'm thinking more. See this person G right here, who the car is headed towards. Right. There's something that. Did anybody run the math to get a negative number? And think, there's probably something fishy about that. I probably shouldn't be getting a negative frequency. And why would that be? Why would that be? has to do with this number right here. Here's the speed of the car, 600 meters per second. Why does that kind of break the equation?
Oh, it's past space sound.
Exactly. Yeah, that's faster than the speed of sound. What's traveling faster, the car or the sound waves it's sending out? The car. Does this person even hear anything? No, no. No, the car reaches him first before he hears anything. Yeah, all right, that was just a little trick. So, yeah, pick up on that. All right, so let's do one of these topics though. So number six, oh, I flipped over to chapter 15. All right, so 15, right this side here. I got a fire truck moving at 35 meter per second. The car in front of the truck is moving in the same direction at 15 meters per second, and so it's slower. A 327 hertz siren blares from the truck. What frequency is heard by the driver of the car? Ooh, so 68. Okay. So we got this truck going at, the truck is 35 meters per second, like interstate highway speed. And then here's this car going a lot slower. The car is 15 meters per second. Okay. This truck is sending out these siren signals, right? But because the Doppler, right, it's catching up to the sound waves it's sending out, causes a pitch shift from the point of view of the observer. So what you guys were using for that whole Doppler page was the observed frequency is equal to the source frequency multiplied by, and then there's this ratio. So the speed of sound showed up here and here. Right, and then there's like this plus or minus. There's velocity observer and velocity source. And whether you apply the plus or the minus on the top or the bottom, well, you had to, I always like to logically work out, like, okay, would this type motion cause an increase or a decrease in the observed effect? Right? So, well, okay, let's see if we can throw some numbers in and make this work. So the observed frequency, right? Now, your book told you the source frequency. It says 327 hertz right there. Right? So that's if this truck is parked and everybody's stationary, everybody agrees it's 327 hertz. That's the source frequency. Okay. We're going to multiply that source frequency by some fraction. All right. Okay. Now here's where maybe we got to make some reasonable assumptions because your book did not tell you the speed of sound. So what do you want to plug in right here about? 340? Yeah, sounds good. Let's do that. That's a reasonable assumption. Okay. All right, and then now observer and source. Oops. Okay, observer and source. Okay, well, here's the values: 35 meters per second and 15 meters per second. So what are you going to put for observer?
15.
Yeah, so we need a 15 right here, meters per second. Oh, okay, and then the source must be the 35 meters per second. So now we got to figure out plus or minus. Let's start with the observer. The fact this car is trying to drive away from the source, in isolation, just that fact alone, did that increase or decrease the perceived pitch?
Decrease.
Yeah, it should decrease it, right? If you're trying to drive away, it should decrease it in isolation. And how would that work out mathematically? Should you add or subtract on top?
Subtract.
Yeah, you gotta subtract. Subtract, because that would decrease. Okay? But of course, that's not the whole story. The other part of the story is this truck is barreling toward the car even faster. And would that by itself cause an increase or decrease in the observed frequency?
Increase.
Yeah, definitely increase. And how do you get an increase? By doing what on the bottom? Subtracting. Because if I subtract on the bottom, doesn't that make the denominator overall smaller? But if the denominator is smaller, what happens to the overall fraction? It's bigger. Okay, get that? So it is minus minus. Okay. Here's another way of thinking about it too. Because I always like to go through that logical process I just walked you guys through. But some teachers teach it like, oh, the fact that both cars are moving in the same direction. See how they're both going to the right? If they're both going in the same direction, then the signs will also match. In this case, minus. Okay. Okay, so they're a little trick. All right, so let's throw that in the calculator and see what we get up. All right. Very well. I got a number that I think looks reasonable. What are you guys getting?
348.
348? Yeah, that's about what I'm getting. 348 hertz. Yeah. I think we got time for one more. One more. Some of these other ones look pretty fun too, but let's do 71 because this is the last lab that you guys did. So this is a good review of that also. A vertical tube with the top of the base is filled with water and tuning forks vibrate over the mouth. As the water level is lowered in the tube, resonance is heard, right, just like you guys did with your lab. When the water level is dropped at 17 centimeters and then at 49 centimeters, what is the frequency of the tuning fork? So let's get a picture here. And so this is like if you had a vat of water, like up to here, there's the water. And what if this height was 17 centimeters? Okay. And then we'll lower the water level until it's like way down here. So now this height is 49 centimeters. Okay. Right, so we're striking this tuning fork. And in both of these cases, it's resonating, right? Right, so the water level is dropping. And it's like, and then when it's getting there, it's like, so both of these points, it's resonating, right?
Yep.
A lot like you guys' lab, right? Now, if I was to draw the wavelength, right, it could look off like a transverse looking wave. Right? Now you guys know it's actually longitudinal, right? But maybe this is sort of a transverse representation of a longitudinal wave. It would look, well, whoops, this a little bit. It should look approximately like this, right? Where really these nodal points represent high pressure point, high pressure, and high pressure, like right there. It's like that. Actually, we had to expand that a little bit because my pipe is a little bit narrow. That's basically I made my pipe wider so it's easier to see. Yes. So really be like that. Okay, that's a little bit easier to see, right? Okay. Now, what do you guys think I should do with these two distances? Yes, subtract them. So 49 centimeters minus 17 centimeters. What's that? That 32, I think, centimeters? Okay. All right, so the difference is 32, which is really like this right here, isn't it? Okay, so that's like this right here. It's like 32 centimeters. Right? And what does that represent in terms of the total wavelength?
Wavelength of one period of.
Oh, yeah.
No, I have to go grab something in the future.
It's half the wavelength. It's lambda over 2. Right? The full wavelength actually isn't quite here. This is a quarter of a wavelength. This is 3/4 of a wavelength. So the difference here represents half of a wavelength. So if you want one full wavelength, guys, what is one full wavelength in this case?
64.
64 centimeters, also called 0.64 meters. Right? Right. And then let's tie this together with speed equals wavelength times frequency. Right. Now, what was the question again? You guys remember what the question was?
What's the frequency?
Exactly. What's the frequency on this tuning fork? It's the same tuning fork. So we're trying to solve for this frequency here. Okay. We know the wavelength. This. Right there. That's the wavelength. Only you need the speed. Well, you know what? Maybe we could come up with a reasonable number. What's a good reasonable number here?
Space time.
Yeah. What do you guys feel like using?
Um,
Oh, no,
Or, I know that's light, right?
Yeah.
Oh, no. 343.
Sure, let's do that. Let's do 343. 343 meters per second. Yeah. 0.64 meters. Okay. And the frequency on this tuning fork. Fine. Alright. What frequency tuning fork do you think that is?
10 hertz. Like 11 hertz.
Yeah, while you guys are looking at, I'm gonna Google the answer for wonder what musical note that is.
Probably low.
Oh yeah.
535.
And I have to make it from the change.
Mr. Griffin.
Yeah.
535.
Yeah, that's what I'm getting too. I'm getting 135 hertz. Alright, and according to Google, it says it's very close to the note C5. So basically a C note. Yeah, there you go. Alright. So do it. All the puzzles we saw some of these a few days ago. Of course, we saw a bunch today. If you want to keep those over the weekend so you can study them, then you can totally do that. For for the quiz for Monday. If you want to turn them in, you can. And then if you hold on to them over the weekend, then you can turn those in on Monday.